Heunen, who's talking about joint work with Klaas Landsman and Bas Pitters.
Yeah, thank you for having me. My name is Chris. I'm a PhD student of Klaas Landsman. And together with Bas Pitters, we've been reading these papers by Chris Isham and Andreas Düring and also the Jeremy Butterfield. And then I was raised in an intuitionistic manner. My master's thesis was in that, and nowadays I do category theory and physics, so that's how we rolled into this. Klaas Landsman is more in the mathematical physics department. Ever since I started my PhD studies, he's been indoctrinating me with Seastar algebras as the way to model classical and quantum physics. And Bas is also very constructivist. And what I want to talk about is the same really as Chris has been talking about. So it doesn't really matter that there's 10 less minutes because he said most of it already. But in our last talk, pretty much all we used of the topos is that the truth value object is multi-valued. It's not just false and true. It's a general Heiting algebra with more structure than that. But topos has vastly more structures. It's been hinted at, this internal language. And I'm going to try and use this language to make more explicit, more intuitive at least, why these constructions look like they do. Yeah. So the plan is as follows. I'm given a Seastar algebra A that's supposed to model some physical system I'm looking at. It could be classical, it could be quantum. And then I'm going to define a topos, depending on that algebra. And inside there, I'm going to pinpoint a certain object. And that turns out to have very nice properties. And from there, we're going to reason about those properties. So, but first, I need to make a bit clearer, I guess, how you reason internally in a topos and how you define objects to have certain properties. So to lead up to there, I'm going to have a few words on categorical logic. And I want to start with the example of a monoid object. I picked this because I guess most people who are familiar with the talks in the afternoon know about monoidal categories. So a monoid, usually in set, is something like a group without inverses. So that comes down to you have some set and I have a multiplication on it and I have a unit on it. It's supposed to be associative and the unit is supposed to be a unit. This I can say whenever I have tensor products in a category, I can interpret an object as having this kind of structure. Because when I say this multiplication is supposed to be associative, that's just a certain diagram that needs to commute. And when I say this unit is really a unit, when I multiply by 1, I get the same thing back. That's also just a diagram that needs to commute. So there I have, 3 equations, the diagrams commuting. And then I want to make a sentence saying this equation holds and this, and that's the property I want of my object. So if I want to be able, in general, to pinpoint an object in a category, and I say I want it to have equational things and finite conjunctions as a properties, I'm going to need tensor products or monoidal structure on it. So if I want to have more, these are very easy properties, of course. If I want to have more involved notions in a category, I need to have more structure on the category to interpret it with. So now we had a very simple language, kind of. You just had type m, a function symbol m for multiplication, small m, and no relation symbol actually. And from those basic formulas I can make, with finite conjunction, I can make bigger formulas. If I want to have more than finite conjunctions, I'm going to get a bigger kind of logic, and I need a more structured category to interpret this in. So the next example is, suppose you have finite conjunction and unique existentials, so that you would need something like that to say what a group object is, because every object has a unique inverse, right? For this, I don't just need a tensor product, I need a proper product, and I also need equalizers. And this goes on and on. If I want to specify objects which satisfy things that I can define in regular logic, that means I have not just unique existential, but normal existential quantification. I need even more properties of my category. And as your logic grows, you also need the structure of your category you want to interpret it in to become more and more. And the summum of this is a topos. This has, as Chris has been saying, it has only a few structural things here, but they're very powerful. The most important is this subobject classifier we've been hearing about. And the combination of these few things with finite limits in the subobject classifier really gives you all of first order and even higher order logic you want. You have all the usual connectives, the and, the or, the implication, the negation, and all the conjunctions, all the quantifications. So now, remember the plan was I'm given a Seastar algebra, I'm going to make a topos, and inside there I'm going to pick an internal Seastar algebra. So first I will need to say in this kind of language what it means for an object in a category, in a topos, to be a Seastar algebra, right? This is a bit of a technical slide, actually the most technical slide, so don't worry. So we've been having this language. It had types, it had function symbols, and maybe relation symbols. And from those basic formulas, we could make larger formulas. Now if I want to interpret the type M in my language as the object M in my topos. And I want to have the multiplication function symbol as this arrow M in my topos that I was talking about. And all of the rest of the bigger formulas are fixed because of the structure of this category. For example, if I have a formula with conjunction in it, then it just gets interpreted by having the finite products. So in particular, if I have and then the interpretation here, if I have any formula phi built up from the basic formulas, this gives me a sub-object of the free variables in it. So in particular, if the formula is closed, that means there's no free variables at all, then I get the empty, how do you say this? The empty variable list. I get a sub-object of that. Let's call that object omega, right? So this means the interpretation of any formula gets a value, so to speak, in omega. So we can think of omega as being the truth values of these formulas being true or false, but as I said, there can be more than that. In particular, we can also wonder when is the interpretation of such a formula the full sub-object, when it's really actually true. And when that's true, I say my topos T validates this formula. And now a surprising thing happens. If you go and check all the usual things in logic you have, like excluded middle, for example, P or not P is true, and you check all the usual P and O axioms, it turns out that the logic of this internal language is precisely intuitionistic logic. So it's constructive. So case in point, you don't have excluded middle and you don't have axiom of choice. This is going to be important later. Okay, so now we can finally say what a Seastar algebra is. Usually, if you encounter Seastar algebras in a first course, it's given as a set with some structure. First of all, it's a vector space. It has a multiplication. And in terms of physics, you should think of elements of this set as observables you can measure. And the multiplication can be either commutative or non-commutative. I didn't specify any of that. And when it's commutative, you get a classical system modeling by the Seastar algebra. And when it's non-commutative, you get a quantum system. This is the famous thing with position and momentum not being commuting. I had an office mate. So when a student says, I don't believe you that quantum mechanics is true, I had an office mate who liked the following analogy. You can do a very simple experiment at home. Either you first take off your clothes and then take a shower, or you can just take a shower first and then undress, and the result will be very different. So this multiplication, is not necessarily commutative. And you have some other structure which is not really important at the moment. Except for this norm here. Notice that it takes value in R. And you want this structure to cooperate in a certain sense. But as Chris has been talking about, R is really a hard thing to consider. Usually when you have a first course on how you actually construct R from the rationals, for example, one way to do it is, for example, with Dedekind cuts. So you say, I have a left half of my rational line, I have a right half, and they come very, very close to each other. There's zero distance between them. You want to formulate the zero distance between, you're using classical logic, the excluded third. So we would like to get rid of this R to say what a Seastar algebra is in a topos. So this is something Chris Mulvey has been working almost 30 years on. The point is, I don't want a function anymore. I just want to say when the norm of an element of the Seastar algebra is smaller than some rational. I don't want to pinpoint exactly this real number. I just want to be able to approximate it from above in this case. Yeah, so all that changed from going from here to here is this R, and of course that C is the same thing. And then these, you have to of course reformulate the way these things have to work together. Right, so now we have the techniques in place. Now suppose I'm given a Seastar algebra in the real world, on the ambient topos, so to speak. We know they model some kind of physical system. And now Niels Bohr says, it's actually a pretty logical thing. If I want to investigate physics and I want to be able to make a real theory, I should be able to tell my neighbor what I discovered, of course. So that means I have to write it down in classical terms, otherwise he can't read it. Mathematically, that translates to I can only get access to the commutative parts of a Seastar algebra. So now suppose A is this algebra we were given, and we're going to consider all the subalgebras which are commutative. This is all the things Chris called the classical snapshots or the worldviews, the things you can actually get at. They form a set in the first instance, and of course these things are ordered, partially ordered by inclusion. One subalgebra can be bigger than another, or they can be totally non-comparable. So in this sense, they form a pre-order, and we make that into the category by saying the objects are just these commutative subalgebras. They have an arrow from C to D, precisely when C is included in D. And then finally, I'm going to consider the category of functors from this context category to set, or D. Set is good enough. And this is going to be the topos associated to the Seastar algebra we're given, which is motivated by this Bohr argument. Now, I can define a very canonical object in here. So when I say what an object in here should be, it's a functor from CA to set. So I should first of all say what it does on a commutative part of A. Well, I have to give a set back, so let's just give C back. And then I have to say what it also has to act on morphisms, of course, being a functor. So that means I have to say what it does on an inclusion from C to D. I have to make a function from C, actually, to D. Well, that's easy, because you have the canonical inclusion. So this is a fine, proper object in this category. Now, it turns out if you formulate these requirements I gave you for being a Seastar algebra in a constructive way inside this topos we've been building, it turns out this object actually satisfies them. And not only that, it's commutative. So that means we were given this Seastar algebra on the outside, we made a topos, and by moving inside the topos, it all of a sudden became commutative. So restricting yourself to this topos we built kind of represents going from the possibly quantum things to the classical things. And I made a picture of this. So this is the topos we're all living in. Let's just for a moment say it's set. We were giving an algebra in here, and then we made a smaller one, so to speak. We moved to that. We picked an algebra in here. Picked an object, and it turned out to be an algebra again. Now we can reason about this inner algebra in two ways, of course. Either we're in this ambient topos, still classical logicians, or we can move into here. That's what Bohr would say, that's what physicists do. They're in here, they can only see the commutative parts. So suppose now we take the role of this internal observer for a while. Now the thing about commutative Seastar algebras is they're totally characterized by the Gelfand duality. They all look like continuous functions on some Hausdorff space in general, topological space, to the complex numbers. So here I've stated the classical version of this. It's an actual equivalence, duality in the categorical sense. On one hand, you have a commutative Seastar algebra, and you can take a spectrum which will be a compact Hausdorff space. But that's the other thing Chris has been talking about. Not just R is a problem, also topological spaces can be a problem because they don't have points. You need the axiom of choice to construct points in a way. So we have to do something about this category here because we can't really formulate it inside this topos we're living at the moment. The trick, and it's a very old idea actually, is not to look at the topological space as its points, but you only look at the open sets. So a continuous function is not a function from the set of points to the other set of points is continuous when the inverse image of an open set is open. And we can just translate this into if you only have the open sets. So you get a lattice of open sets on the receiving end and a lattice of open set on the giving end. And then you have a lattice morphism going back. And these things are called frames or locales depending on which direction you want the morphisms to go. And this form of the Gelfand duality is something Chris Mulvey has been working on for 30 years with Banaschewski. And they have a proof of it which works for any Grothendieck topos. And then Bas Pitters and Thierry Kuka generalize it to any elementary topos. So that's great. We can apply this to our internal commutative Seastar algebra now. Why does it keep doing this? So when you apply it to our, where is it? The inner Seastar algebra, you apply this Gelfand duality, you get a topological space, a locale. So this is kind of the phase space, the configuration space which tells what the world is like for this algebra here. This is something people have been looking for ever since von Neumann. It's the whole business with the contrals was invented because of this. And here is such a thing. And the point about this thing is it's very funny. The Cauchy-Specker theorem is Cauchy-Specker, but in the analysis by Chris Heisman and Jeremy Butterfield, it says these things don't have global sections. But now this thing is a topological space, or at least the open sets of it. It actually has no points at all if it's when it's a proper quantum thing we're looking at. So you have a kind of phase space, but you can't pinpoint the way exactly things are. You can only approximate it openly with an open set around it. Okay, so now we're here. We were giving an algebra, we made a topos, and inside there we had very funny objects. The other holy grail you want to do, of course, once you have a phase space is when you have a state and you have a proposition, you want to pair them to have a probability, for example, or to see whether it's true. So this is the last part I'm going to talk about. So let's start with states. You have this external algebra. Suppose you have a state on it. We have to convert it somehow to the internal world first before we can talk about it, because that is where the phase space lives. Now, a state is just a function from the algebra to the complex numbers that happens to be positive and linear. Likewise, you can talk about integrals on any space, for example, which the internal Seastar algebra is. An integral on that is also a function which is linear and positive. So it's not surprising that you can prove that a state on the external thing is precisely a one-to-one correspondence with an integral on the internal thing. So a state on the outside we can consider in the inside world as an integral, or people who've been taking courses on integral and integration and measure theory note this is the same thing as a measure. A measure says how big a set is, kind of. And you can also make a valuation. It doesn't say how big any set is, but it says how big an open set is. You don't get a number out how big it is, but you can only approximate it from below, which is this funny symbol here. The whole space is size 1, so to speak. The empty set is size 0, but you can only, it gives a lower part of the rational line, not precisely a real number of the size. So the thing to take home of this slide is, if I'm given a state on the external algebra, that gives me a map internally from this phase space into kind of the interval 0, 1, but approximatively. And the other thing is these observables. This is where the Dasonization thing comes in. So the observables are just self-adjoint elements of the external algebra. First we have to convert them again to the internal world. But this is a bit hard to do because, so we're given a little a in here and we have to say what it does there. That means we have to say what it does on each commutative subalgebra. But the problem is this element of a might not be in C. So the best we can do is approximate it on either side. You have every Seastar algebra self-adjoint part has this partial order you can use. So the best we can do is look at all the smaller things which are in C and all the bigger things which are in C. When you write down the type of what this object should be, there's this funny left-right arrows there. Remember when I talked about how you usually construct the Dedekind reals as cuts of the rational line? Well, this arrow precisely does that. When you have any partial order, the line here, Q, I can consider the left halves and the right halves, and I want them to be open. I don't want them to end precisely at a point. But I now drop the requirement that they have to come infinitely close. And these things are, I call them cuts, just Dedekind cuts, but not the Dedekind property. These things this is what I mean by this left-right arrow. So of course what you can then do is you take the rational line, and you take the cuts of it without this Dedekind property. And that gives you can put a topology on it, the information topology, so to speak. You say a point is in this interval here. You get more and more information, and that gives you the open approximations. Yeah, so now we made a little a here into an internal version, approximation, but we're going to go further than that. On each point of this approximation, I can let loose my Gelfand duality again. So that gives me a frame map, or so to speak, a continuous map from the phase space to this approximative real object. Yes, so I'll just get to the point. Remember, every external observable gives us such a map, every state gives us such a map. And when I have another thing about this rational object in there is that it's constant. So when I have an external interval, I can just make an internal version of it easily. So I have these three kinds of maps, and a physicist would really like to know what the value of this proposition is, so to speak, or the probability. Well, I can just compose them, and I get a map in my topos from the terminal object to this approximative probability 0-1 interval, which is just a probability, right, internally. But we can even go farther, and you can see, you can check whether this probability I'm given is precisely 1. This is, because you can only approximate them, this is an abbreviation for all n, it's bigger than 1 minus 1 over n. But you can just consider it. And that gives you a proper truth value as a morphism from the terminal object to the truth value object. So it turns out this phase space sigma is this very great thing to have. And this is the point where I get to the conclusion. So this topos Chris Isham has been talking about, we can make it, you make it part based on a system, a quantum or a classical system, and doesn't really matter. And via very canonical constructions, you get internally stuff which looks intuitive, and it actually gives you these truth objects. So it's not really a weird thing to consider. They did a lot of hard work to find this underlying sigma phase space, but it really rolls out if you look at it properly. And that's what I wanted to say. Thank you for having me.
Questions, comments? Thorsten?
Just when you talk, I wonder, this construction, you have this, Seastar algebras, you look at the commutative subalgebras, and then you find that inside this topos, the thing is commutative. Yeah? Is this an instance of sort of more general construction? I mean, do I have to look at Seastar algebras? Or
No. You can do this for anything you can frame in geometric logic. When you, for example, when you take any group, you take all its abelian subgroups. Internally, this gives you an abelian subgroup again. So you can do it for more than Seastar algebras, but this is just the case we're interested in, that's all.
But I think the thing is, can you build from external information, internal information, which is interesting enough, because if you take an algebra with only a trivial subalgebra, commutative one, then
Yeah, yes, you can. The problem is going back up.
yeah.
You can't really do that. At least I don't see how. That's the whole point of quantization, I guess.
Yes, so you're looking at arbitrary functors from your
Mm-hmm.
process of Seastar, commutative subalgebras to sets. Now I think that process has got directed unions, I think.
Which one?
If you have
Oh,
directed
this-
union of commutative subalgebras, then it's still a commutative subalgebra.
The CA has directed unions.
Yeah, so you've got a DCPO there, and I
Yes.
conjecture also it's an algebraic DCPO because you can take finitely generated commutative.
I'm not sure, but it could be.
So I was wondering if you thought of going to the instead of functors from CA to set, look at the continuous.
Which preserve the DCPO structure, you mean?
Right, yeah. So you'd be looking at sheets over the algebraic DCPO.
So that way you would get an even more structured version of the Bohr argument, you mean? Yeah, I guess that's possible. But I'm not a philosophic person myself. I really like to stick to the details, and I know this is something class came up with, the Bohr interpretation. But you will have to justify it some way or the other. I'm not sure which way is best either way.
Okay, so now we close this first session and we migrate in first. Thank you again. We go up to the 8th floor, and I just recommend to follow the locals.